Okay. All right, let's get started, guys. It's our third lecture, and we're going to talk about application of data science in retail, right? Retail data science. So first of all, let's start with defining what we actually mean by retail. And I mean, obviously, of course, each of you are very much familiar with retail. It's the stores we go to where we shop. In general, retail is sale of consumer goods or services through a particular distribution channel. And that can be, store, it can be, catalog, or these days, a lot of things that's happening online. But the point is that retail is a sale directly to consumer, right? So it is in between the retailer and the consumer. And of course, there are multiple retail type of stores exists, but typically they're classified in several segments. One segment is usually called CPG, FMCG. It's grocery, it's a food retailer, and all kind of mass merchants like Asham in Russia. Then there are sometimes the fashion apparel department stores. There are specialty retails. That's usually what we have in the malls, and of course restaurants, cafes, all kind of fast food. Now, CPG, FMCG is probably the sort of the most widespread type of retail, and FMCG stands for fast-moving consumer goods, and CPG is consumer packaged goods. So sometimes those abbreviations use like synonyms. But the point is, the specificity here is that, first of all, as a consumers, it's usually frequent or regular purchases, like daily consumption. Food, you go buy milk, you go buy bread. It's also characterized by low prices, so it's usually sort of quite cheap. The items have very short shelf life, and sometimes perishable items, sometimes not. But again, think about food, and it's really in an area with low customer engagement, because when you go shopping, you put some effort into choosing, but you definitely, when you buy your next car, you spend a lot of time thinking about it. When you buy furniture, you think about it. When you pick up toothpaste, well, one brand or another, you probably decide in a second. And if there is the brand you used to, well, you'll just pick up a replacement. And very typically, there are a bunch of competing brands sitting next to each other on a shelf. Now, for retailer, it's actually not an easy thing to work in this FMCG. In FMCG, because first of all, it's always a high volume, right? It makes sense. You make money when you have high volume of goods, because it's a pretty low margin business. So you make very little money on each item sold. Quite often, FMCG has a very extensive distribution, and extensive distribution means quite complex logistics and pricing and many other things. And it is high inventory turnover, which means you need to replenish inventory quite often. And you cannot have a lot of gains, especially, you have to have a large variety of the items, but at the same time, you cannot always have a large stock on the items, simply because it can be perishable like food. So there is a lot of specifics in FMCG, and data science is often needed there. In general, it doesn't matter whether we talk about sort of brick and mortar store, which is regular stores, or we're talking about online. Retail supply chain is always quite similar, where you have a sort of manufacturing part, starts with raw materials, then the supply provides it to manufacturer, then items being produced, send to distributor, or usually it's called wholesale supplier, and then they resell it and distribute to retailer, and then it ends up in the hands of the customer. And so it's a retailer's job to match supply and demand, right? Customer demand, how many items and at what price customers are ready to buy, and the supply of the items, the supply of goods that they need to carry to satisfy that demand. And obviously, this balance between supply and demand, that's defines the price at which the retailer can sell the item, and eventually dictates the profit retailer makes. And when today we hear a lot about breaking down of supply chains, that's what it is. That's a chain that's being broken down. And though even we can have stores open, there'll be nothing in there because either no raw materials or no manufacturers or no way to deliver and distribute items. So what kind of data science problems, what kind of data science tasks one can work on within this retail world? First of all, why retail? Well, because that's where there's really lots of data available. And so retail is really a sort of big data world. So we just saw that there is this logistics or operations side, so supply side, and then there is a demand side. And within the supply side, it's really about logistics, delivering goods. It's about buying in bulk. It's about predicting how much you need to buy. So and the first thing to do is try to predict the demand, right? What the demand on the different items would be. And it can be seasonal, it can be event-based, etc., etc. Then, based on the demand forecast, you can try to build a sales forecast that will tell you, how much money you can make, and what kind of store supplies, what kind of inventory you need to carry, and that's brings us to this buying volumes, inventory management. So, how many of which goods, of which items to carry. Then there are sort of a little bit more strategic, can be more strategic questions like store location optimization. So where you actually have your stores and which stores you close, which you expand. If you're a large brand with hundreds of stores or even thousands of stores, that's quite important. Then there is a question always about price. So what kind of price you offer? Yes, of course, it depends on how much you paid, how much they pay for the goods, but at the same time, depending on the price, demand can change, right? And so it might be better to sell more volume at a cheaper price, at some discount, or other ways around, right? And again, a lot of items are seasonal. So and you observe this on a regular basis in in the stores when items goes on sale, but it's really depending on the retailer. It's either store level management or upper management that decides actually sort of which items would go on sale and what kind of sale, right? And so then there's this big question of what's called markdown or promotion. And the question is, yes, you can have some sort of gut feeling that like, yeah, let's give a 10% discount, but you can actually calculate the optimal, you can measure the effect and you can calculate the optimal value of the markdown, right? And choose the right items to mark down. And finally, there is, of course, supply chain optimization problems, right? So how to deliver, when to replenish the stock, and how to do it optimally. So that's sort of operations. And there is a big overlap here in between, like data science in terms of predictive analytics, but also operations research optimization problems. On the right-hand side here, I'm showing customer demand side, and it's usually quite a lot of discussion about marketing. And of course, the king right now is personalization, which means personalized service, personalized items, recommendation engines, that based on your on a past customer behavior suggests sort of other items to buy in the future. And of course, that's sort of very, very popular, became very popular online when it became easier to actually track customers. But that the same thing happens with loyalty programs, right? And so if a store can track the customer, it surely does it. A market basket analysis tells you about, and this is more sort of older traditional technique, similar to recommendation, where it analyzes the basket and sort of the items that bought together and can suggest you to buy some item based on what you already have in your basket. Cross-sell and upsell, this is a selection of either selling you some sort of more expensive version of the product you're trying to buy, or product with some additional features. And cross-sell is selling you, offering you a product that you might want to buy from some sort of different category of products. Propensity to buy is trying to calculate the probability, the likelihood that a customer will buy a particular item depending on its price. Well, loyalty program optimization, again, it's sort of, first of all, designing a loyalty program, and then depending on that design, right, and based on particular customer behavior, what kind of rewards the customer is going to get. So again, typically in retail, for retailers, the loyalty programs are quite easy, but say airlines have very sophisticated loyalty programs with different types of upgrades, etc. And Starbucks created a loyalty program with games embedded in them, and all of them are not just sort of designed by intuition. They're actually calculated, very well calculated, in terms of what kind of profit they can bring, expected profit from those programs. And finally, it's a customer sentiment analysis. So right now, of course, again, the retailers want to understand what's on customer mind, and which is usually can be expressed through the customer sentiment, and whether it is social media or any other sources. Cross-selling market basket analysis is not the same thing. Cross-selling is selling a different item, right, from a different category, and market basket analysis is understanding what's in your basket, what to add there. So it's it is sort of similar in the sense that yes, it's all looking for potential additional item to add there, but in market basket you often think about a combination of things. Personalized marketing, next best offer, also quite similar things, where you talk about the next offer you can get, and the most likely offer somebody is going to buy. Or when you talk about personalized marketing, you often discuss the whole strategy of how to approach it. And quite often when you build model, it's not only next best offer, you kind of build out the entire, say, pathway for a person, right? How to converge somebody onto a particular purchase. For example, let's say if somebody is a avid coffee drinker and you go a lot to, let's say, well, Starbucks you don't go these days, but you go to I don't know, some other coffee store, but you buy cheap coffee, which is not espresso based but sort of cheaper version. Well, obviously for a coffee shop, it would be beneficial to make you switch to more expensive sorts of coffee, which is espresso based. Well, you can probably come up with a strategy of, giving a few free shots of espresso somewhere in between your regular purchases, right? Trying to converge you into sort of espresso drinker, et cetera, et cetera. So it's more of sort of not only just one-time story, but a long-time story. And difference between CPG and FMCG, well, there is a subtle difference. Again, FMCG is usually stands for fast moving consumer goods. And that's stuff that goes, fast from the shelves. And that's what you usually buy, what you usually use in your daily life. Consumer packaged goods, that is something that is already sort of prepackaged, consumer goods, but, some of them can stay in the store for years. It's a bad idea, but for some longer time. But, it's a subtle difference. Usually people, use both of those acronyms when they discuss it. So but the bottom line here, guys, is the following. Whether we look on the left-hand side, on the right-hand side, it's always the same story. First, you want, eventually what you want is you want to make money, right? And making money while increasing revenue or reducing costs. That's all it's in there. And that happens due to optimization. Now, you can try to optimize your today's operation, which is good, but the reality is you really want to optimize the future operations, because while you're optimizing things will change. World moves, right? You start optimizing your store, items in your store in spring, but then, hey, it's already summer and the temperature is much higher and people buying a lot of, say, iced drinks. So the point is, you want to start with prediction, so trying to see what's going to be happening in the future, and then you optimize for that future, right? And that helps you with increase of revenue, reducing costs. So yes, optimization for today's conditions is good, but it's better to make predictions and then optimize for the future state of the world when it's possible, right? It's not always possible, obviously. Okay, going back to sort of practical things, retail, I would say retail, if you think about, use of data science, probably the most advanced data science today is used in financial industry, in banks, and in telecom operators. The reason being, well, they historically, reach in terms of the data, and historically they had a lot of data people. Banks has been doing risk modeling for a very long time. Obviously, telecom operators also dealing with data, so pretty much everything is being recorded. And I would say retail is sort of next in line in terms of the advanced data science methods, and especially, of course, online stores. And it also comes from the fact, well, that there is a big volume of data, that all the transactions being recorded, and the data usually is well structured, which means it's identical data that being collected for each purchase, or the data that exists in the warehousing systems for for sales, or for items that you have. SKU, the acronym or SKU, the acronym, it's stock keeping unit. It's usually the unique number that is assigned to an item, and typically that's sort of what that's how you kind of distinguish items. And typically, again, there is a sort of customer data, which is usually stored in a CRM systems, customer relational management. By the way, there are a lot of acronyms, obviously, in any sort of business field, but they sound scary, but when you kind of Google them, understand them, they're just, okay, it's customer relational management software, right? That's CRM. So customer data, it's usually the data on the particular customers that tells you, okay, on which date, which store, what items, SKUs, usually how many, purchased by a particular customer. If the data exists, that sits in CRMs, and, if there are loyalty programs, that's where it goes to. And there is usually a sort of store sales data. Most of the time, it doesn't have any information from customers, right? It's just sales. But it tells you a lot of statistics about sort of items, units, how much money, et cetera, et cetera. And then there is, of course, sort of back end or back office data on the sort of all the supply and warehousing data. So all that information. Plus, quite often you get data about promotions, about marketing, and today there are a lot of sort of external data that can be available. Somebody's asking if future prediction always necessarily based on historical data. Within the machine learning framework, data science framework, you usually look into history so your past predicts your future, right? But you can come up with the models that might again, you somehow need to build these models. You can come up with a model that is not based on the data, but that will be already not data modeling, but your sort of economics or intuition based modeling. And again, data modeling works well in a predictable world, in a situation that has been seen before, and when things change sort of smoothly. The situation of black swans, right? When there is unexpected events happens, that's when all models fail. And we're right now actually facing that situation in Russia, when of course all the credit models fails, and pretty much any prediction model fails today because of the activities in the last 2 months, because of sanctions, et cetera, et cetera. So in this sense, yes, you build the models on your past data, and the models can predict the future, but under the assumptions that historically you have seen all the possibilities, or almost all the possibilities. And if there is a situation come up that the model never seen, right, never trained on, of course, it will not be able to predict correctly on that situation. Okay, so here is just a few examples. Again, it's very illustrative. We're not going to go into details, but just to give you a sort of a flavor of what data science is doing. For example, inventory management. So the idea is that you do need to keep some inventory, goods at stock. And you don't want to have a lot of them because, well, you're often buying them from a manufacturer, or if they give it to you for resale, well, then you still pay some money for that. And you don't want to have a very, very large stock because it's, taking warehouse space. It's the money that you put in there, they're being wasted. So you want your stock to rotate quickly. At the same time, you don't want your shelves to be empty, right? So you need to very well design how much stuff you keep in stock. Then you need to keep in mind also, supply time, delivery time, et cetera, right? So to do this, you need to understand demand. And so again, it starts with planning the demand, predicting the demand, and on the top we're showing some sort of demand history for certain items in a certain store. And then there is ordering policy, right? The brute force ordering of sort of, yeah, let's just fix, order all the time the same amount of stuff. It's easy, but it's not optimal, right? So then you need to decide, okay, how much you order. Then there is a delivery time, a delay. So there are quite a few computations that goes into play. And then inventory picture here just shows you the drop of the inventory. And then you can sort of try to do simple modeling and say, okay, if the inventory drops below sort of X items, then you order. But it doesn't always work that way, because again, you have seasonality changes, you have certain events. Imagine, and I mean, it's a true fact, right, that when there was a World Cup in Moscow and in other cities several years ago, a World Soccer Cup, the demand and consumption of beer increased dramatically, right? And even the planning was poor, a lot of money has been lost, or actually not made on a beer, right? And those things has to be taken into account. Another example just shows you that there are even certain things that sounds pretty easy. In fact, when you investigate them in depth, there are a lot of details. For example, you know, the stores do promotions, right? And they do promotions, of course, eventually to, you know, make bigger profit. And some promotions are well designed, others maybe less well designed. And the question is how to measure the efficiency of the promo, right? Or effectiveness of the promotion. And you can think about this by, you know, looking at this picture. If I look on the left side, here, you would say, okay, look, let's say, you know, there is some base sales that I usually do, and then due to the promotion means, you know, drop in the price. Okay, then there is this additional sales we made, right? So, okay, well, great, that's how much money we made. But at the same time, you need to understand that, yes, promotion means really discount, which means you're giving away some money, you're giving away some profit. Okay, so that drops, and the way to read this, yes, this is how much money you made. This is, well, that's how your discount, how much money you spend on the discount. So eventually, that's how much money you made for real in the promo sales, if you take into account, you know, how much money you gave away because of the discount, right? Because if you were selling at the original price, that would you would make that much money, right? Okay, you can stop there, and you know that's a good start, right? But then there are other effects, and you know, one of the sort of well-known effects is called cannibalization, right? Where your regular sale decreases due to promotion, which is, for example, you know, if you buy, you know, you go to the store, you see something on sale, you know, you buy more, for example, items of that type, but you don't have enough money to buy something else that you actually were planning to buy, right? And so that decreases your sale. Or for example, you know, you typically buy, say, you know, one brand, and then there is another brand on sale. Yes, you know, you buy the one that's on sale, and you cannibalize sales of the other brand. And then there are other promotions running, right? You never see one promotion in the store, so then there is a competing promotions. And again, with a fixed amount of money that the consumer is willing to pay or spend in the store, you know, then the promotions start competing, and so they're cannibalizing each other. So eventually, when you take all that into account, all of a sudden you realize that the net promotion effect is really much smaller than you know, you would think when you just say, okay, look, let's multiply the delta in the price by the volume of the items we expect to be sold. So you do this type of analysis, right? Then you realize also with you look at the price, demand price elasticity, and seeing that, like, okay, if we drop by that amount of money, if we drop price by that amount, you know, how much more demand we get. And you can actually calculate this. And you know, in a good advanced settings, pretty much you need to do this upfront before you launch a promotion, then to actually realize, okay, if it's going to be beneficial or not. All right. So these are just sort of very, very simple examples of, you know, how you can use data science in retail. Yes, the other thing is you're absolutely right that buyers can stockpile things and then decreasing sales, right? So that's going to be a, you know, another sort of way, right? So you pretty much suppress the demand for next, you know, 3, 4, 5 months, like saying, I don't know. Yeah, probably that's not going to happen with bread, but with toothpaste or toilet paper, yeah, people can buy it for half a year. Well, you know, is it better to have markdown on all items at the same time? Look, I don't know. That's it really depends on sort of the strategy that store has. But, you know, my point here is that there are a lot of things you can actually calculate, right? So yes, you can, you know, you can do things with by intuition. And later on, you can come back and say, okay, look, let's verify my intuition and do this kind of analysis. But it's better, of course, to run this kind of analysis before you jump into all kind of promotions, especially if it's like 30% or 50% discounts. Okay, so that was a short intro into this whole thing about retail. The good news also about retail that a lot of sort of fields within the data that comes from retail are quite self-explanatory. And because we're dealing with retail on everyday basis as consumers, it's easy to understand sort of what's happening. And so I don't think it needs more of the attention now, but you will have a chance to work on the retail data later on a seminar and within the homework. And I want to switch gears right now and go into the actual, data science things. Okay, so one thing that I also want to emphasize before we go into the modeling is this notion of learning on the data. One thing which is very, very critical and important to understand that whatever model we use, whatever model we build it on a limited amount of data, right? We never have all the data that exists out there on any event. We never have it because, well, first of all, it's not only because, you will never get all the database that the store has, for example, but in general, there is never all the possible things that could be recorded, actually being recorded or actually happened. So the data we deal with is usually a subsample of the all possible data. Hold on a sec. There is this new vanishing pen. Let's see what it does. So there is this always, like lots and lots of data. Let's say this is all the data, all the possible data that exists in the world. But we always, work on a small subsample. That's the data you have at hand, right? You never have this sort of whole world of data. If you had, it wouldn't be a model, it would be the real world. So within the small sample, we usually split it into, two parts, and we use one part to train the model and to predict, the values that we didn't give to the model, which is, what sort of train and test is. But keep in mind that eventually we want to use this data in our model to predict what's happening here, what's happening in the real world that we never seen. And so that's called generalization. That means how your model behaves on the data that you never seen. And it's very important to understand that it's pretty much always will behave worse in the real world than on your little piece of data that you train it on. And moreover, it's not necessarily the case that if you make it work perfectly here, it will improve performance there. It can actually be quite opposite, because you will memorize what happened here and it will not generalize well on the unseen data. And we'll be coming back to this story several times. I'm going to emphasize it a couple more times today. But now, again, remembering that we have, where did I go? Right, so we're starting, so this is the data that exists in the world. That's the data that the data scientist has. And, data scientist has to train the model and test the model on the data he has. So then we take this data, we split it in two pieces, we train on one piece, we check, verify the quality of the model on another piece, right? Now, one sec, I need to move the screen. Okay. Now, this is this train test paradigm. When you actually build the models, you actually do this. You train the model and you build the model and you check how well the model reproduces the training data itself, the one you trained on. And that's called training error. Then the second part of the data that you had, the test data that you never shown to the model, you check it, you check how well your model performs on the testing, on the test data, and that constitute test error. Now, training error will always be better than your test error, simply because, you know, that's the data that model seen, and this is a data that model never seen. And then obviously, when you launch your model on the data that sort of never been even close to you, then the performance will be even worse. But this is something you need to remember, that when you train the model on some data sets, you know, you expect, even if you get your training data to 0, it's actually a very bad thing if you get your training data to training error to 0, because that's called overfitting, and that usually means your model will perform really badly on a test. So what you want is, you want the training error, you want to keep some training error, and you want testing error to be, you know, of the similar, it will be a little worse, but the similar to training error, and that's sort of your optimal story. We're going to talk about it on examples on next several slides, but this is probably the most important part for the entire sort of supervised learning, right? How to handle the errors and this whole train test paradigm. So let's go back to regression, right? And if you think again about retail, right, there are a lot of things we can try to use regression for. You know, we can think about you know, predicting the demand. We can think about the predicting of, you know, sales based on advertising. We can think about the calculating on the customer response rate, you know, et cetera, et cetera, et cetera. So these are all numerical values, and you know, it's a regression that would allow us to calculate this. And we started talking about regression last time, and so what you want to do when you build a regression model is, when you have some data points like shown here, you want to predict what would the value be at, you know, some point where we don't have the answer, right? So for example, let's say, you know, again, this is this TV advertising data set where you predict sales versus how much you spend on TV advertising. And let's say, okay, let's say there is this amount of money being spent, and let me change the color, being spent on a TV advertising. Well, what sales would be? Well, you can say, okay, well, look, that's our model, you know, that's the read of our model. So, you know, looking at this from a mathematical point of view, this is interpolation. So I try to interpolate inside the data, or if I say I want to understand what the response would be here, or that's sort of extrapolation, I'm going outside of the data. And this whole thing about building a model is trying to select an optimal model that eventually will give you the smallest, you know, possible error, right? But the smallest error on the real world, and the closest for us into the real world, is a test set. So how do we evaluate the quality of regression? Well, we talked about this last time. The way to do it is there are different metrics, but the point is, you know, if you choose the model, say, for example, like here being a straight line, then at every point, you know, when you make a prediction with this model, it's you know, different from differs from the sort of actual value, and that the difference is an error, right? So for example, the actual value here is right there, but the model would predict here. So this distance is your error, right? The actual value is here, the model predicts there. This distance is an error. You might think like, wait, why do we want the model that sort of so much off over there? Why wouldn't we sort of draw a line right here? Well, we can do that, but then it increases errors for all others, right? We'll make error bigger here, error bigger here, error bigger here, et cetera, et cetera. And so the sum will be greater. So we select the line that gives us the smallest deviation, right? The smallest error overall for all these data points. Now, of course, you can select not necessarily a straight line. You can go for models more complicated, right? And instead of straight line, get some sort of curved line, and that will reduce that error. But then we get into this discussion of, okay, is that complexity of the model, and if this is a really behavior that you expect, right? For example, you might expect quite linear dependence in between, amount of TV advertising and how much, people buy your stuff, right? The more you show on TV, the more people buy it. So over there, you might expect linear dependence. And so you might not want to go for a model that is more complicated than that. Now, let's say we have a regression problem. And this is how we approach the model. Let's say we have this data, which is, quite nonlinear the way you look at it. Now, what I have done here, I did this 80-20 split where I took the data and split it into the training set and test set. Training set is blue and test set is green. And so ultimately what we eventually want to do is, let's say if I want to use a straight line as my model, I want to select, and the way it's going to operate, the way it's going to work, we'll build a straight line that gives us the best fit to this data. For example, it's going to be this line. So we calculate some of the distances to each of the point in the test set, in the training set, right? And we draw a line that will give us the smallest value for the error. Maybe this line, or maybe, maybe it's a little bit too high. Maybe it's this one, which will be the optimal. So we'll select the optimal line. And then we calculate an error here, right? There will be some error. But that error is really error on the training set. It's not the error that we will observe later on in real life. And the best approximation to the error that we'll observe in real life, the quality of the model, will be performance on this model on the data it hasn't seen before, which is this green points, right? And so we take this line, that's a line, that's a line, and then we measure the performance on this subset, on the test subset. And again, I probably draw it too high, but anyway, we measure the performance on this subset. And the error that we get here, this is the error you need to pay attention to, because this is an error that you most likely, that will be the best approximation to the error you will see in the real world. And this is an error that, we need to pay attention to, right? So having a small error on a test set, on a train set is good, but your eventual goal is, of course, small error on a test set. All right, does make sense? Well, I hope it does, because this is sort of this is the core. Now, here's an example. I tried to model this data with linear regression. On the left-hand side, this is actually computed. This is not me just drawing it, arbitrarily how I did on the previous slide. This is actually being computed, right? And the way it's done, all these errors, some of the squares of all these distances to this line has been minimized, and that's how this line has been drawn, right? It's out of all the lines, it selected the line that gives us the smallest sum of those distances. And this is the error we got. Now, we take this line and then we verify it. So this is the train data, this is the test data. We verify it on the test data. Notice that the test error is larger than the train error, the way it should be. It's not much larger, which is good, but it is larger. And so this is a performance that we would expect from a model on the real world data. I mean, on the real world, again, it's going to be at least as good as this, but most likely worse than that. So this is an error, you're looking, this is an error of your model, right? The error on the train set, this is just something that's only important for you as a designer, as a sort of data scientist that creates models. Now, having said that, okay, fine. You know, I can go and argue that linear regression is all I need, simply because, well, it's very simple, and because I do believe that there is a sort of linear dependence. But looking at this data, maybe, you know, maybe linear is not the right model, right? Maybe you need to go for something more complicated. Let's see what happens if we go. Let's see what happens if we go for sort of a better solution. Let's go, it's the same data. And instead of having a linear regression, I would say, let's go for, you know, polynomial regression. Polynomial regression is different from linear regression, is just by the fact that instead of just having, you know, straight line, and so having just one coefficient, we have actually the polynomial. So there is, it's going to be, you know, x squared, x cubed, et cetera, et cetera. So here is, we model it with a parabola, right? So it is, you know, x squared values. Here we take the polynomial of the 5th degree. Here we take 10th degree polynomial. The higher polynomial we take, well, the more parameters, right? So you know, the 2nd degree polynomial p equal to 2 means you calculate 3 parameters. P equal to 10 means you calculate 11 parameters within the model. And the higher the polynomial degree, the more flexible the model is, right? Sort of the more oscillatory it's going to be, the better it's going to feed the data, right? But then what happens? Look, we look at this. So first of all, let me go back for a sec to the previous slide. Remember, train error 0.96, test error 1. Okay. Let's go for higher degree polynomial, right? We take polynomial of 2nd degree. The train error drops and the test error drops. So it's a good sign, right? Now, we can go for higher polynomial degree than 2. It's 5. And by the way, of course, looking at the picture, you realize it actually describes even better. And really, train error drops and test error drops, which is very good. But let's say, okay, well, look, if life is so good, let's just sort of keep increasing the polynomial degree, right? And let's go for 10. What happens here is, well, your train error went up and your test error significantly went up. So this really tells you that you overfitted the model, which means you tried to reproduce your training data pretty well, but on the test data, it starts failing because you kind of memorize the data points that the model says. So looking at this, and without knowing without any background, like I don't know what this data is about, right? I don't understand it. But just by looking at these numbers, I would say, yes, this will be the optimal model for me because it has the best, you know, train error and what's most importantly, the best test error out of the models I have, right? Now, having said that, if you have a context around it and you realize that, look, you know, from the sort of fundamental science, and again, whether it is supply demand or something else, you believe that the model shouldn't be, you know, higher than 2nd degree, well, then you stick with the 2nd degree polynomial, right? Or sometimes, you know, this change from here to there in terms, I'm sorry, from this test error to this test error, this 0.2 drop, you know, it can be good looking on a paper for a data scientist, but it might not be valuable for a business. It might not affect the business that much. And so because you don't know what it's used for. So that's why, as you remember, you know, in the first lecture, we talked a lot about data scientists understanding the business context and understanding, you know, how his model is going to be used. So sometimes, you know, taking this linear regression model is the best, right? And again, to build linear regression, you need less data than to build, you know, any of those models. So that can be the best answer. Okay, but maybe you can go for even better. maybe you feel that, look, like in Google, you have, millions of views, actually hundreds of millions of views, and then even, 1,000th of a percentile point can mean a lot of profit. So you want, the best, the most precise model possible. So a different model is called K&N regression model. This is a model that instead of just calculating polynomial and choosing the best parameters of the polynomial, this model, just a very simple thing. It takes nearest points and calculates average, right? And say k equal 1 calculates, the nearest point, average k equal 5, it takes 5 neighbors, k equal 10, it takes 10 neighbors. And then I just sort of interpolated it here, so the solution will look like a line. And again, k equal 1, train error is 0. Why? Well, because we send the line to the point itself. So on the train data set, the model performs perfectly. But, on the test error, on the data points that it hasn't seen, the error is very large. We can take, 5 points to do averaging. And here is the train error drops, test error. Of course, again, a bias train error, but it's also small enough. And we can go for 10 points. Here, notice what happens. Again, train error increased and test error increased. So the point being, again, what happened is we went from the model that is too rough for this, right? Too inflexible, too rough and sort of not enough flexibility for the model, to here, this model is, too refined. I would say, it's just too much, actually other way around. So this model is averaging too much because it takes 10 neighbors. So it takes pretty much this window, right? And this model is, too fine in the sense it just takes nearest neighbor. And so it creates you these oscillations. And, somewhere in the middle here, this model is optimal in terms of the performance. But again, guys, the key here is this number. So you need to have this number low. This you will never have this test error small if you don't have train error small. But what makes sense is, of course, you check your model on the train, and if it is small enough, then you go for the test model. For the test error. Okay, now I have a bunch of questions here. Give me 1 second. How much test error is considered acceptable for a model to be a good fit? Again, like this is a business question, right? You can think about relative metrics. In absolute, it's really the question of what units you use. If it's relative, we talked about this R squared as a measure of the quality, and that's a relative value. And so you can think about it independently of the units you use or problem you solve. It's usually R squared is, from 0.8, 0.9 is, considered pretty good. Yes, number of parameters, nth degree polynomial plus 1. Yes, because there is this parameter. If you have, remember, linear is ax plus b, right? And it is first degree polynomial. And there are 2 parameters, a and b, right? Or ax squared plus bx plus c, which is a parabola, second degree, and there are 3 parameters, a, b, and c. We search for the smallest test error. Eventually, yes, we search for the smallest test error. That is absolutely correct. But you usually measure first of all, you measure the train error, because this is the data you train on, right? And then you check the test error. Eventually, yes, you want smallest test error, but the test error will always be larger than the train error. Yes. Can stock price be an example of applying K&N regression? Well, the stock price is extremely hard to model because it's actually a stochastic process. There's a lot of randomness in there. yeah, you can use K-NN regression. Train error is always smaller than test. Yes, it's better be, right? I mean, unless there is some sort of accident. I mean, you accidentally can get the test error smaller, but you know, then you sort of, like we did before on the previous lecture, we talked about that in sort of in the real world, right? You do cross validation, which means you do several different splitting, and then you average the errors. And when you do that, your test error will never be less than the train error, well, unless you make a mistake somewhere in your calculations. Okay, so here is yet another example. We're still staying with the same data set, and here is yet another modeling techniques, which is regression trees. Now, by the way, notice that polynomial, you know, especially if it's linear regression, it's easily explainable, right? You have those two coefficients, and you can say that, okay, well, this changing proportionally to this number. With you know, this K-NN, it's very hard to explain. There's no parameters. It's really, and in fact, you know, with when you build the regression models, your model is that set of parameters, right? You calculate them. That's all you need. When you deal with K-NN model, K nearest neighbors, the data is the model itself, because that's all you need for any time you want to calculate some value. You need your data set, because you need to find the nearest points. And regression trees, this is just a tree, you know, the way we think about trees, but in that tree, in the leaves of the trees, there are values, right? And so, for example, here's an example of the modeling of this data set with a tree. So what does it mean, modeling it with a tree? Modeling with a tree means the following. Let's say I want to have a tree of the size, and tree meaning decision tree. So if I have a tree of the size of the depth of the depth of 2, and I want to you know, do the simplest possible model. So what I can do is the following. I can say, okay, look, I know that in the leaf of the tree, I should have the value of the function that will be model, right? So if I take a tree of the depth sort of 0, that really means taking an average for this data, right? And literally take average and assume, let me clear this, and then our model will be replacing everything, let's say, with this average value. And I can calculate the error. Well, I mean, you know, it's a model, right? It's just sort of taking, instead of calculating all kind of different things, I'll just say, okay, we'll just use average as a model. It's going to be baseline. But then I would say, okay, look, I want to do better. To do better than that, the way to do this, I can, for example, try to split my data into 2 parts, and, you know, take average for each part. I can say, for example, split it in here and say, okay, there were points here, so average will be somewhere here, and I will replace all the data points with that average. And here the average is, you know, that's the average. And so if I want to answer what would the value be, let's say if I ask what would the value be, what the y value will be corresponding to this value of x, I will go to this line and say, okay, well, this is the value that's going to be, right? And if I take this, I go to that line, and that's the value will be. So this is my partition into this sort of 2 spaces. And that's what's reflected here, this partition in 2 spaces. But what I can do is, you know, instead of just sort of randomly, like I did right now myself, drawing this partition in sort of a random spot, I can calculate the optimal position, which is, okay, if I have to split this data into 2 pieces, I still can minimize the error, right? This prediction error. And, you know, if I do that, the split will be for this particular data. Here is, well, here where the split is going to be into those 2 spaces, right? So space 1 and space 2. And here it corresponds to space 1 and space 2, where average value here is 19 that's this value, and value on the other side is 17, that this is a value. And the way tree operates, when new sample comes, it says, okay, if let's say I put here x equal to, I don't know, 30, right? Then according to this condition, it will go to the left-hand side, right? And if it's here, and so it's going to be predicting this value, right? This value. Okay. And if x is, say, 50, then we'll go to the right tree, and the answer will be this. Make sense? Okay. Yes, please.
Two questions. What does MSE stand for in this flowchart? And can leaves also have further leaves within them?
Yes. Okay. Yeah. So the answer is, so MSE is this least square errors that we did. Just give me a sec. We'll go back. Okay. Mean squared error, right? This is MSE. Oops. Draw. That's MSE, right? So if I go back to that slide, it is the distance. So we calculate for each point, we calculate the distance from the point to the line, right? And do the sum of the squares, and square root from that. Okay. So it's exactly the same metric as everywhere else. Now, can we do it further? Yes, that's exactly what we're going to do now. Is this tree corresponds to literally this split, right? But then we can probably, we can split it here more, we can split it here more, then we can split more here, split more here. And so we can actually keep splitting and making it a smaller and smaller pieces. And that's how we can build the model. And that's actually the tree, right? This is kind of this, I think it's called the stub. It's not a real tree yet. So if we go and go further and build a tree, that's what's going to look like, right? Now it splits into 4 pieces. Now those nodes that were leaves before, now they're sort of intermediate nodes, and these are the leaves, right? And the way to parse this tree is, again, you take this, if x is less than 42, then we look onto this side, and then let's, for example, x is greater than 7.5, let's say x equal to 10, then this is the value, this value corresponds to this line. Okay. It's here, it's not vertical. The only reason is because that's sort of how I visualized it. The right way to visualize would be, of course, that the partition should be vertical, right? It's just not the best visualization. But anyway, so yeah, we can go further, and we can get more and more precision out of this. But remember that having a more flexible model is not always the best, right? Remember, there is this always train and test sets, and you can add flexibility, but you can memorize the data and you can screw up your test set. And so first of all, here's the regression tree, right? I make it more and more large, larger and larger tree, a little bit more and more complex model, more and more flexible. It will produce data better and better, right? We will hit more and more sort of data points, but as a result, we might end up again in troubles, right? So look here, if we go, and by the way, remember, it's the same data set we started with today. So, train error here is not bad, right? The tree depth is 2, so it's just 2 layers. And it's already pretty good, right? It's sort of 1 leaf, 2 leaves, 3 leaves, 4 leaves. And, it's pretty good train error, pretty good test error. Now, I can go on a higher depth, so it's a deeper tree. So now we have 16 points here, right? And train error dropped, but test error dropped not that much, right? So train error dropped because now it's kind of reproducing those pieces well, but it's kind of overfitting already. But then what happens if I increase the depth and so get even bigger tree? I can drop train error almost to 0 here, and we never seen this before. Well, actually, we have seen train error 0 on KNN, but it gets very, very small, but the test error increases, right? And that happens again because this is what's called overfitting, which means your model is very flexible and you make it follow the training data too well, so it cannot generalize, right? Generalize meaning perform on the data it hasn't seen. And so again, there's sort of, the best is somewhere in the middle. And as we discussed previously, if this is a good enough for you, so within this particular tree approach, right, you can, by looking at the prediction of your model, by looking at the train and test, you can actually, decide that this is optimal sort of among tree models, right? But then you had KNN model, and previously you had polynomial model. And we can go back and look at the test error for each of those models, and then decide, like, if you really don't care about, say, explainability, then, for example, those models, sort of, it's only the quality of the prediction that matters, right? Then you can go and check, okay, test error here 0.65, test error here 0.62, test error here 0.68, right? So, this is the best test error. So probably, out of this 3, if the only thing you care about is sort of the quality metric that we consider here, probably you would choose KNN regression as a modeling technique to solve this particular problem, right? But it might be that, look, here, with trees, you get slightly worse test error, but it's a tree, and so you do understand why certain decision has been made, right? Why the prediction it did was the way it did, because it actually gave you this partition. It says, like, hey, here's the rules: x less than 42, x less than 0.75, then that this is the model we choose. I'm going to answer your question in a second. Now, trees are actually quite, they're very powerful, right? And that's sort of one of the oldest techniques in the data science world, sort of as old as a regression. But I would say, even more powerful is what's called ensemble of trees, where instead of having one tree, you use several trees and then you average out results. Now, there are 2 approaches. One is called random forest, another called gradient boosting decision trees. They're slightly, so that they're different and similar, and they're similar in the sense that both of them using groups of trees to make predictions. They're different in terms of how they're constructed, but the point is they're using some sort of voting mechanism eventually. And so the idea is that instead of having one tree, you create a bunch of trees by taking subsamples of the data and sort of creating several models from each subsample of the data, and then averaging the results eventually when you try to do predictions. So then you sort of send your new data point through each of the trees, and then they vote for the result. That's how it works in random forest. In gradient boosting, it works differently, but again, the idea is it's a bunch of trees. So when you do this, notice what happened. You actually had a pretty good train error, and you have a very, very good test error. So in fact, just from practice, random forest and gradient boosting decision trees, they probably work the best. So, you can go through all the other techniques just to make sure, you're convinced that you have selected the best model. But typically, these are 2 models that work the best in real life applications. Now, I'm not touching here on deep learning. If you have a lot of data, that might actually beat the random forest and gradient boosting, but here it is sort of the typically it's sort of no-brainer to try one of those on your data and expect good results. Those models are quite stable, but there is also a drawback, right? When you have sort of random forest as is, it's not, the results are not very interpretable because you have a bunch of trees, and those that you can have like hundreds of trees it can create for you. And so it's not very easy to interpret. But again, if you want just a very good prediction, stable prediction, that might be your model of choice. So finally, to sum up, and that's again, probably this is sort of the most important slide for the lecture that you need to kind of keep in mind always when you build models. And this has to do with both regression and so for both supervised learning, so for regression and classification, there is this training and testing, and it's, you know, there is also a scientific term for this, bias variance trade-off. The idea is the following: when you have your data and you split on train and test, and you verify your model. So what we have observed, and I hope I convinced you by those examples we've seen, that when we increase model complexity, the training error tend to drop. So model complexity means polynomial degree, right? It becomes higher, or you know, depth of the trees becomes sort of deeper. We can actually drop significantly prediction error, and we can go right to zero, right? Especially remember on KNN when we took nearest neighbors equal to 1, right? So you take model, you make more and more complicated model, more and more complex, more and more flexible model. You will drop your error eventually on the training sample. You can drop it almost to zero. But what you do care about is not that error. What you care about is the error on the test data. And that was going to be happening. It's going to be when you make more and more complicated model, the test error will be dropping. But then when the model becomes too complicated, too complex, too flexible, the test error will be growing. And we observed it in 3 examples. And so this is your sweet spot. That's the model complexity you want to select. Whatever sort of model you use, you know, random forests, you know, random forest or decision trees or KNN or polynomial, that's where you want to operate. And you will observe this gap, right? Training error will be much smaller than test error, right? But then you will see that your test error is dropping and this gap increasing, right? And so you need to operate somewhere right there. So if you increase the model complexity, both of your errors will be dropping to some moment, but then training will keep dropping, test will kind of level out or even start increasing. Then you just should stop and not go for more complex model. And I think this is sort of the key message here, right? You always look at the test error and be ready that it will be dropping when you increase the complexity, but then it will go up if you do sort of everything right. And you know, you choose that sweet spot right there. Okay. Let me go to your questions. Random forest, that's the second model is gradient boosting decision trees. GBD usually, right? Gradient boosting decision tree. It's just sort of different. I mean, it sort of uses different idea. It consecutively builds a tree, but it's also the more stable version of sort of, you know, more advanced version just than just a usual regular tree, right? It's sort of gradient boosting. Usually it's called gradient boosting or gradient boosting decision tree. In scikit-learn, it's called XGBD. So, you know, that's sort of the method of choice together with random forest, this is the method of choice for data scientists. Yes, I haven't gone in the discussion yet to this sort of train, test, validate, not to complicate the issue. But yes, you know, if you split into 3 data sets, yes, you can use a validate to tune up things in terms of parameters for the model. But again, this test that is something that your model shouldn't see. And this is your sort of best verification of the model quality. How in depth rate calculated? Depth rate, you mean like how deep the tree you choose? Yes, it's again, it's a parameter of the model. You select it, but you know, you can, you know, sometimes it can be done automatically through this on the validation set. But the point is, you can actually run it like increasing the depth of a tree, right? And monitoring the error, the test error that you're seeing until you realize that, look, it's too deep. You start losing on the test error. Yes, the deep stands for the number of layers in the tree, and the number of layers it's a binary tree, right? So the number of layers really corresponds to the number of leaves that you get at the bottom of the tree, right? So the more the depths, you know, for the binary tree, clearly it's 2 to the n the number of trees. Should we split it only vertically? Well, here it was this vertical split only because it was X and Y, right? So it is only one dimensional. When you have, you know, if it's not just one variable, but many variables, those splits are multidimensional, of course. And I think, yes, I think I answered all the questions. Any other questions? All right, good. And we're out of time, so you will have a seminar starting in 10 minutes. And thank you, guys.
Thank you.